Oh, hello. Welcome to the Analyzing Architecture Systems lecture. I'm Leland and excited to go through one of my favorite topics, which is how systems are manifested in architecture, as well as how they're used to aid designers to accomplish the goals that they're looking to accomplish. So I think that you're going to enjoy this very much, hopefully as much as I enjoy it. So we're going to learn what systems are. You probably have a notion of what a system is. I mean, you made it to college, but we'll be speaking to systems more within the domain of architecture and how architects use them to understand and make buildings. 3 parts overview. We'll be looking at 2 kinds of systems. This is my own dichotomy, but systems that are based on parts and systems that are based on frameworks. And you'll see what I mean by that in a bit. So the overview. So what is a system? A system is one of 2 things. It's a configuration of parts which work together to achieve a goal. Parts aren't necessarily objects in themselves, although when you think of a kit of Lego, each Lego is a part. But when you think of the systems of your skin and hair, you can't really point to a part that represents your skin. It's kind of like a kind of continuous component. You know what I'm trying to say. It's tough to think of parts without thinking of discrete objects, but it can be so, and you'll see some examples of that. And the same parts can serve roles in multiple overlapping systems. So it's not like if you have a design that has multiple systems implemented in it, it's not that each part can only participate in one system. So for example, car body participates in multiple systems. So parts is one way of looking at systems, but the other is, not just in how systems are manifested in the thing that is being created, but how systems are used to actually make the thing that you're trying to create. So in a framework, an agent, you as the designer, superimposes a construct on material. So grid systems, for example, which are these kinds of virtual datum geometries where you're snapping things to minimize the amount of unique spacings and locations, is one such framework. And when someone operates systematically, what we mean by that is that they're operating within a framework. So there's a set of rules or methods. For example, Marie Kondo and the KonMari method to clean rooms. You probably know a little bit about that, what sparks joy and what doesn't. Here's a simple way of looking at it, since those 2 cover a lot of bases. Systems relate parts and goals and frameworks and goals. So I've drawn this little simple flow chart here. How do parts accomplish a goal? Well, they accomplish a goal with the system. How does a framework accomplish a goal? Well, framework accomplishes a goal with the system. That's one way to think of it. So the system is the edge between these 2 nodes. A good system is one where the parts work harmoniously, or when a framework reliably produces a desired outcome. So the word system is used so much. I just forgot my AirPods case. It's used so much. I'm not going to talk about. I'm not going to use that word. I'm just going to use the words parts and frameworks. So I'll try to avoid the word system because it's used in so many different ways, right? Here's a little bit more about systems, although this won't be brought up through the lecture, but open and closed systems, it's about causality. So an open system can be affected by outside influences, and a closed system is cut off from forces outside of the system's parts. So when you play pool, that's theoretically a closed system, but there are caveats such as the humidity that can affect the play, the boards, the table setting, all that kind of stuff. We'll assume that we're operating within a closed system, although design is not a closed system. And you'll learn that when you're older and you have to make a building for somebody. So common systems. So this is the way I break down systems. I look at them in terms of parts and frameworks as we discussed, but within those 4 categories. So parts, you have styles and orders, assemblies, diagrams and grids and construction geometry for frameworks. Within each of those, you have two. So what are part-based systems? Styles, orders, modules, and structural systems. And frameworks, so ways of working, the partee, the layout or circulation diagram, grid systems, and construction geometry. So quite a little bit to go over, but hope this changes the way that you think about how systems manifest in architecture. So we're going to break down these common systems, starting with styles. So, what is a style? Like the word system, it's used pretty loosely. When we say something is a style, we mean that there's a unique way that it is done. So to be stylish is to bias towards a unique methodology, to kind of break the norm. A style, generally, like in architecture, you would use it to say that it expresses the character, time, and place and authorship in media. That could be in a drawing, that could be in the building itself. But in architecture, there's usually a coupling with place and time that creates style. So different regions of the world at a certain time might have done things in a certain way architecturally. So in the discourse of architectural styles and their function and relevance, probably has been going on for much longer than here when it was recorded, but the earliest recording we could look at is Durand, and it was built upon by Semper. So these are the round temples plate. So Durand made these amazing plates of these older buildings. So a lot of Roman architecture and just trying to figure out, well, how do I start to categorize and understand these architectures? So here's some Roman temples. Looking at it in terms of style, there's a set of rules that are being played out here across different scales with regards to the spacings of these parts. And by parts, I mean in particular, these posts and lintels and these walls. So how does style function as a system? You might not think of style as being something systematic, but think of it as a set of parts which divide and fill an underlying structural and spatial diagram. So all architecture has one kind of key goal, which is to stand up. Hopefully it does that. Maybe there are a couple of exceptions where buildings don't stand up and it's okay. But I can't think of any right now. That's extra credit. But beneath that is a structural and spatial diagram that Durand was trying to get at. So all of these things kind of follow the same underlying kind of structural concept, which is this post and lintel system. And there are different takes on that system. So how is that kind of diagram, I use the word system, I apologize. How is that diagram filled with material? So these are looking at a few different diagrams that are filled with material. You have the post and lintel as I showed. You have this more kind of triangular hut style. And then in the last, you have this punch through a wall. So the punch through the wall, just trying to create a way of looking through, or, have some air move through a barrier. Different ways of doing that, which inevitably might be just turned into two posts and a larger lintel. When you make the perforation through the wall hit the ground, that's what you end up with. So this is interesting. This is, I believe it's still under construction, although I haven't checked on it, but this is in New York. This is David Adjane Hill West working on this. What's really interesting about this building is that it's flipping between in one of the diagrams that we're just looking at, in fact, this kind of post lintel, archway going down to the ground. Once you hit a certain level here, it turns on its head and doubles its width into the structural bay, which makes sense, that you could have more perforation towards the top because there's less material above this point that needs to be supported. So you need less structure if these walls are in fact load bearing, which I haven't checked. You have these interesting tapers. I think there's a future slide with Taipei 101, where we look at references to pagodas and stuff like that. But yeah, typologically, you have a kind of post and lintel paradigm occurring here. But then once you get above that and the bay enlarges, that kind of arch curvature just becomes decorative. So it's really behaving more. It is post and lintel, but just across a wider span. But it's treated more like a punch out in a wall rather than the confluence of structure. So at the top, you would understand it as a whole, a set of holes. And yeah, here you go. So we were just talking about Taipei 101. Every 8 floors, there's a outrigger truss, which brings it back to the central core. And at the moment that occurs, the tapering is reset on the section, and you get this kind of spiral column or pagoda style. And what's interesting about the pagoda structural topology is that, and I think that there's some controversy on this, but it was designed to mitigate earthquakes. And there's this idea of if you taper out the walls of the building, that you'd be able to balance the building. But I believe upon analysis, it's really this central core and always kind of tying back into that core that gives you better luck in an earthquake. And of course, there's a giant mechanical gadget somewhere around here, which is the tuned mass damper, which is resisting the movement of the tower. So orders. Orders refer to something very particular in architecture, which is the Roman analysis of ancient Greek architecture. In fact, when you Google ancient Greek architecture, I just highlighted in red the usage of the word order. When the Greeks made buildings, they didn't really think that what they were doing was making orders. All this is an analysis done in the future. So it really is true that the people that write the history books have the control. So classical order systems are styles. They're decorative parts, structural and decorative parts, excuse me, which divide and fill a post and lintel system. What's the goal? This is just my interpretation, but the different orders have different slenderness ratios. So I believe it's standardizing the way that detail is applied and the connections which are used for certain ratios of structure. And to aesthetically and narratively express what the Greeks are trying to express. So 2 of these are Roman, which are the Tuscan and the composite, but the Doric and the Ionic and the Corinthian, I believe you can find in ancient Greek architecture. They have different average heights when deployed, but over time, especially with neoclassicism, this kind of strict relationship between slenderness and the order and the style of that column is kind of messed up. And the deployment of these orders, as you might have already learned, or you will learn when you learn about neoclassical architecture, starting with, I believe, Germany, it's really about expressing civilization by referring back to Rome. So expressing a sense of, this is civilization. So modules, something that has probably come up in your design course one way or another. A module is a part which functions either wholly independently as part of a whole or somewhere in between. And the exciting opportunities are somewhere in between. So if you break off a piece and it's isolated, it has this capacity or set of capabilities. But when aggregated together, you've probably heard that word aggregation a few times. When brought together and joined with other parts, you have some that's greater than some whole that's greater than the sum of its parts, rather. Modular systems tend to be economical. That makes sense because you're just making the same part over and over again. And in terms of the reading of it as once it becomes an architecture, the part similarity highlights the kind of overall gesture and the relationships and adjacencies between those parts. subtle differences, slippages, negative spaces are enhanced, and the usage of modules can change conditionally based on orientation, relative location on site, stuff like that. And that's really interesting. So you have the same part that's just somewhere else and maybe in some other orientation, and that performs a different task. A few examples of this at different scales. So Su Fujimoto's Serpentine Pavilion 2013, really interesting. It's this metal box with glass. So sometimes there's a glass panel in there, sometimes there isn't. But the repeated, I think that the same stick is used over and over again. The same glass panel is used over and over again, and it creates this larger formwork. The Holocaust Memorial here by Peter Eisenman in Germany. This is, of varying different heights, the same kind of block here that's tiled across space, modulated in height a bit. Very kind of claustrophobic, hedge mazy experience going through here. Really gives an interesting affect when you go through it. And then you got Puma City. So low tech, if you're not familiar with them, they are known for using containers in their designs. In fact, if you visit their office, and I believe this is still the case, they have bins and bins of blocks. I think they're foam, sometimes of other materials that they just they just lay them out on the table and they play. And the block is the same scale, the same proportions as the shipping container unit. So this is Puma City, really great one. You can find photos of like hundreds of people standing on this, so it's really quite strong. And they're using an economical module, which is this shipping container box. Bjarke Engels. So the innovation from him and his studio is looking at the residential unit as a module, and then having that module kind of tile across a form. So a lot of his buildings follow this kind of simple system and deliver a really interesting greater effect. Here, he's kind of pushing in every other unit like a checkerboard. That gives you some exterior space. And the way that he expresses his design methodology is usually a narrative that begins with some form making set of operations, and then the discretization of a result into units, which are usually residential units. So you may have heard this really interesting story about why trains are the scale that they are, why they're the width that they are. So the first trains were pulled by humans, but then I think at the same time, or maybe shortly thereafter, they were pulled by horses. So the idea of a train actually predates the idea of the motor, which drives the train, the engine that drives the train. And you would have these, metal rails so that you'd minimize the friction of the wheels. You also constrain the direction so you could move things back and forth really effectively. People, by the way, were killed all the time by these things, even though there are lines in the ground. That's just the way things were back then. If you want to see an interesting story, you should look up the, I believe it's like the West Side Cowboy or something like that in New York. There's a guy on a horse that would chase the kind of street trains around the meatpacking district and yell at people to get off the tracks. It's amazing. You got to look both ways. So because it was these horses that were pulling them, you wanted the horses to comfortably work without stepping over the rail if the rail was raised. In this case here, it's embedded into the ground. Of course, this design had some flaws where, for example, if something gets into the groove, what are you going to do about that? So we quickly iterated on that. This is an animation I put together. The blue box represents the scale of the horses. You have the horses centered on two lines. So really the comfortable distance between two horses set the proportions for cargo, but also the rail sizes, which I think in the United States is 4 feet 4 inches apart. The proper term is track gauge. So track gauge is 4 feet 4 inches. That's between the two parallel lines there on each side. When you rotate that and you make room for parts and the kind of considering turnings and making sure that two cars don't hit each other or affect each other. And of course, these distances have all been dialed in. what you realize is that, well, the width of two horses has greatly influenced the landscape of the Earth, because they're the underlying module is the original force of locomotion in the train. They're the original module for, by which all these other dimensions were created and based upon. And so literally just by that is you can see that the Anthropocene is tiled by this kind of underlying module of the horse. And there's also the example of the space shuttle. You probably heard of that one, but you could look that one up too. It's really interesting. So I would argue that toilets make a big difference too. So the rules around accessing bathrooms and minimizing, usually people want to minimize the space. Developers want to minimize the space of the bathroom. So you have more space for everything else. It leads to these generic kind of layout combinations of bathrooms. It's not to say that a big bathroom isn't great. I like a big bathroom myself. But it does have a big influence on the layout and design of floor plate in residential developments. So on the right here, this is a typical unit designed by Full Stack Modular, which is a company that pre-builds these spaces and then cranes them into the building. It's really fascinating. You can use block instances in Rhino. Those CAD blocks of toilets were 2D, but there's no reason why they can't be 3D. And you can use them effectively to kind of tile and enclose a space. And then when you manipulate the block instance, you'd manipulate the result. So that's using the same block, two block instances, just reoriented. Structural systems. It's a structural system when the architecture is shaped and controlled by a configuration of structure. And Ino Engel did a really fantastic breakdown of this in the track system book. Highly recommend having it. You may be able to find it online, but I won't tell you where. He classifies structural systems in 6 groups: form active, vector active, surface active, section active, height active, and hybrid. Height active is an interesting one. It really is about a different set of concerns coming into play when you start to get into the slenderness of a structure, getting high and dealing with those problems. Hybrid is also an interesting category because it's just the category for mixing and matching previous categories. I think the initial 4 is really the ones that are the most thought provocative and thought forming. So form active, you might be familiar with Gaudi. This is what he's all about. It's where the form that the architecture takes on is behaving structurally. Vector active, so when you draw the forces that you're trying to deal with in the structure, and you kind of literalize those forces as members, and you end up with trusses and things like that. So you have the forces running through the vectors of the structure, and there's a back and forth relationship with that. Section active, this one is pretty obvious. So we shape beams and members the way we do because of the moment of inertia, which you may have learned about in statics if you didn't fall asleep. So that's another one. Surface active, folded plate, awesome. You got a saddle here, also great. You got the surface behaving in a way that's structurally, useful. And height active, so you have this problem, anything tall, if you've lived in let's say like a tropical environment, you've been down to Florida, you see like a crazy wind come through, you see the swaying of the palm trees. Well, buildings want to do that too. So you got to deal with it. You got to get that vertical force to the ground right quick. And you also need a stiff central core or even exoskeletal. When you look at the super tall buildings, because their slenderness ratio, one of the things that they often employ is either a incredibly strong core at the center that's small, but in a lot of cases, and this is true of the Vignoli building, it's at 432 Park, the structures move to the outside of the building. So the wall is load bearing on the outside, exterior load bearing wall, exoskeletal structure. So why is that? Well, then the whole structure is like a column, right? So the moment of inertia of the building, and if you're familiar with that, the distance from the center is a huge driver in how much capacity it has to resist bending. So you just move the structure further away from the center of the building and get better effect. That's what this is describing here, more or less. And hybrid is you know what a hybrid is. So we've covered styles, orders, assemblies, and parts. So we're going to get into frameworks. Parties. What's a party? You probably made one of these already. It's a design system where you make a kernel of intent and you express it as a sketch or a model or a diagram, and it becomes like the source of truth for the project. So this is what I'm trying to do, and you're trying to express it in the same way that you would if you're pitching like a TV show or pitching a business plan. There's the elevator pitch, right? It's like the short and sweet and really dense statement that has all the information that could be further expanded into the project. So parties themselves are usually rendered quickly because they have to be simple. But to make this like a Renzo piano party sketch, to make that requires tons of iteration. Like you don't just sit down one day and you just draw that in a coffee shop and you say, oh, figured out the building, right? Like this is one of possibly hundreds of tries, where each one is not good enough, and then she or he who is creating the party gets some feedback. So it's a great feedback tool. They range in their specificity, but they're usually focused on form and layout, where the rest is up to interpretation. So in this party sketch, you don't really know anything about the facade, and even the roof is a little bit questionable. And then when you use them effectively, what's great about parties is it centralizes the understanding. So I think it's a boon to collaboration. Although in some cases, a party can also be confusing because, a bad party can just be confusing because it can be interpreted in multiple ways. So that's the result. And it's tricky. A lot of architects these days, they do something sneaky where they design the building and then they draw the party afterward. But I believe Renzo. And you can see the similarity between those two things. Perhaps even gave up on this like split level difference between the tops. As you start to expand, this kernel into the building, you realize once you've brought into scale what you need and don't need. These kind of columns here were nixed, didn't even need moment bracing here. So you can see the differences between the assumptions here. Knew that you had to have some kind of projections here, and this kind of inner, really interesting inner space here, really fantastic and interesting place creating here. Not the Kimball Art Museum itself, but the extension for 10 points, if you can name the architect who did the Kimball Art Museum. This party sketch is operating at a different scale, which is why I included it. It's riffing on the original, which you should know who designed that one. But you can see that Renzo here is considering that the most important unit of this is the gallery, and working back from the gallery to kind of tile this matte building across repetitively. Oh yeah, really controversial. So when I was a student, we didn't talk much about Frank Gehry, although he did come and lecture. It's kind of a bad word. And I can see why. I think a lot of people take the wrong lesson from Frank Gehry's work, which is that architecture can be anything that you want it to be. I think that his critics say that the building is really unconstrained. Now, I'm not. I'm including him here for his interesting novelty in the party sketch, which is that usually when people are making a party, they're trying to draw the building. And when you look at his work, the building he's trying to build the drawing, right? His company is Gehry Technologies, right? So he's literally saying, okay, here's the thing, I did it with my hands, go figure out how to make it. And that has been a boon to progress in architecture for sure. And you can't put that down. The use of kind of NURBS curves all comes back to this, which were originally used in aircraft, and the creation of technologies to build these things. So they literally built the tools to figure out how to do this. And I admire that kind of pursuit. Layouts. So a layout framework is where you have a kind of scheme, circulatory scheme, or a set of adjacencies that are productive, and you use that to control the form making and decision making of the building. So the architecture in the end takes on a shape that's deeply related to its function. So a lot of modern architecture follows this layout framework in conjunction with grids and modules in a sense. Extreme approaches to this kind of way of working, the systematic way of working, are literalizing a programmatic diagram as a building, which you might have done accidentally as a student, but is a valid technique in some cases. One of my favorite buildings of all time, and it should be yours too, is the Tuberculosis Sanatorium by Alvar Aalto. Really great. You have a single loaded corridor, and the way that he thought about this was that the machine is part of the healing process. So when you're in one of these bedrooms as a patient, you have direct access to sunlight and nature and stuff like that. So you'd all be facing this particular direction. And he's included it in the extended kind of wing here in these drawings in here. So really orienting people towards nature and integrating it as part of the healing process, which is fantastic. And a lot of hospitals kind of follow this single or double loaded long corridor. Sometimes it's a long bar, sometimes it's bent into a shape where the corners become some kind of egress strategy. This might be one of the greatest cross sections of all time, at least in my opinion. Unbuilt building as well, which in a way makes it even more impressive. It's the IB Museum of Art and Technology by DSR. Technically, Renfro wasn't a partner until 2004, but this is 2001. But still, that's the company. What's going on here? So you have a circulatory strategy that cuts program in half. So you can see it in the GIF right now. You have presentation is gray and you have production in blue. And that's a ribbon. And anything that's on the blue side of that ribbon becomes production. Anything that's on the gray side of that ribbon is presentation. So you're integrating these two programs by zigzagging through the building. Now that's really interesting. That kind of belies this intuition that we have that if we want to have programs in a building, we would have these volumes. Each of them would be programmed differently, and then we combine the volumes in a way and in some kind of order, stack them or whatever to get an architecture in the end. Now, instead, what this is saying is the building is a boundary or a kind of closed region, and I'm going to divide that region with some geometry, and then whatever the number of regions that I create as a result of that boundary splitting across the larger region, the kind of discretization of that region, each of those subregions, and I know I'm using the word region a lot, I apologize, each of those subregions, of which there are two in this building, get a different program. And so they are nested into each other, they're interlocked into each other. And paradigmatically, the idea is to synthesize these two. So production and presentation go hand in hand with each other. Fascinating project. Definitely take a close look at this drawing because it's absolutely gorgeous. It's just got the right blend of everything from my standpoint. Yeah, that'll be a timeless one. Grid frameworks, similar to modular frameworks, but instead of replacing a repeated part, you have this datum line that's controlling other parts. Site conditions can drive grids, but usually there's some kind of metric. It might be based on the part, it might be based on some ideals. When it comes to ideals, look no further than Korb, where he developed this grid system that integrates proportions of the human body. So the building is driven by these kind of anthropological proportions, rather. So when things follow a grid, they tend to be these are just expressions, but silent, balanced, harmonious. So when you lay things out in a grid, there's kind of a stasis. And then when you have something that breaks that grid, that thing becomes contrasted without even changing the part. So that's one opportunity in grids that's exploited. A lot of times in practice, grids are used to ensure that the drawing and the building conform to regulations. So if you have a setback or something like that, you'll have that datum line represented and you'll make sure that nothing crosses it. Grids aren't a novelty, always been used, makes total sense when you're building the thing, make your own building. And you're definitely going to want things to go in a line, that's for sure. So you got this Samaria della Pace in Rome here on the left. You can see the kind of cloisters here taking on this grid at an angle here. I think that's just integrating back in with a road in the city and following that grid. But even so, like you can see the polygons in here, and then the emergent grid lines coming from the midpoints extending from those geometries, the discretization of those edges of the geometries as well, creating subgrids that go into these little chapels here. So been around for a while. I think this is the 1500s or something. Wexner Center for the Arts. So that's Ohio State. Peter Eisenman, and yeah, what can you say about Peter Eisenman? He loves his grids. Instead of thinking of parts being laid out in grids and conforming to them, he thinks about architecture resolving conflict, and the conflicts are manifested by these grids. So each of these grids is kind of conflicting thing. So in the end, the building is this product of these resolutions and intersections. Sometimes not super resolved. And I think that one way of justifying that take is that a lot of his buildings aren't up today. And sometimes there's funny things that happen. Or if you have two beams just like sticking through each other and stuff like that, you just got a column sticking through a floor plate. It's just like, yeah, he likes that stuff. It's an acquired taste. And you have the Parc de la Villette by Bernard Tschumi. Might have seen this precedent already. This is operating at a much larger scale, but parks usually aren't grids. Well, I shouldn't say that. Depends on what the paradigm is for laying out the park. But what he has is this grid array of these follies that's superimposed upon kind of more haphazard and exciting layouts and curvatures. Well, this is Cellular Automata, because this is Conway's Game of Life. If you haven't seen this before, what's happening is you have a grid and tiles can be on or off. And based on whether or not tiles are on and off, you have something. Well, let me try this again. Based on whether or not tiles are on and off, there's a set of rules that determine what will happen in the next frame. So this is kind of a happening frame by frame by frame. I think they're called like generations or steps in a sequence. So each next step derives from the previous step by running the set of rules against these kind of grid conditions here, on or off. And that determines whether or not a cell will be on or off. So it depends on how many neighbors it has. This is called the Game of Life because I think that the more neighbors that you have, the more cells will be created. But then there's also like overpopulation. So it's like how these kind of populations control themselves based on density. So you see the left one is not super exciting, but the right one is an example of a construct that was discovered when this game was made by, I think, a student called the glider. And the glider, it's this Tetris piece with a dot in the corner, and that thing will go on forever. So it's really fascinating. There are other kinds of such entities that will live forever in the game. There's actually a gun that creates gliders where you have a couple of these other shaped gliders go back and forth. Really interesting world if you haven't looked into it. And last but not least, construction geometry. So similar to grids, but you're using an underlying geometry to guide the placement for stuff. So local parameter coordinates become key here. So the curvature that's measured in surfaces and stuff like that, when you get into more advanced 3D design, you'll know what a U and V is and what a T is. Maybe if you pick up computational design, geometry, and parametric workflows, you'll have to know those kinds of things. But you're creating geometry that creates other geometry. It's true of grids, but instead of thinking of a datum line that's more numerical and one-dimensional, you're following a manifold, or you're following a curved line that is usually discrete. I wouldn't say that the use of a field fits within this. It's something different. A field is a grid, but it's distorted. Anyway, it's a long story. Fields are a little bit of a different thing. Let's focus on construction geometry though. So it's a common CAD design practice. The underlying geometry that you draw over follows some set of rules. Maybe it's like a primitive shape, like a very simple shape, like a circle or a set of arcs, and then everything is based on that. So the asymptote Yas Hotel, the exterior skin here, which is integrated with lights, is a surface that is stretched over this, slightly more normative, but when you look at this bridge, not super normative um, hotel structure here. With these, it's a really interesting one. You see it. This is in Abu Dhabi. Sea Cathedral. That's another example of one. So you have this underlying shape. I couldn't find even a Detail magazine like a really great drawing of this. But you have, if you offset, take this shape and elevation and you offset it back into the center, you will theoretically get what the wall conditions on the inside look like. But you have these acrylic tubes with seeds in them that are sticking out. And you get this really awesome effect here. When you're on the inside, this is what you see, all these seeds kind of pointed at you. And it's done really well. This kind of technique is popular. I think maybe right now a little bit less so, but kind of having a guide surface where you have objects that are arrayed on that surface that are shifting gives it a cool parametric effect. This is the roof house by Milo de Malo in Russia. Most well-known of them might be the Gherkin. So it's it's not technically called the Gherkin, but everyone calls it the Gherkin because, well, it looks like a gherkin, and that kind of answers its own question, right? So you have this gherkin shape, and then all the structure and facade follows that gherkin shape. At the bottom, I love this part. Oh, you just have this beautiful set of columns that are popping out here in the atrium. It's great. Currently under construction in Beijing, the Z15 Zoom Tower by TFP. You'll find that high rises in general follow this kind of construction geometry rule. And here's why. It's because the the testing of form when it comes to the wind, when it comes to just the structural topology, those things will guide the overall shape more than anything else. An architect might want to do what an architect wants to do and get an engineer to figure it out. But in a lot of cases, engineering has more of a voice when it comes to the skyscraper. So these things have to conform in some way to the forces that are on them, especially if you want to get super tall, like this Z15 tower. So that's just, they figured out, like a car body, the optimal surface. And also, like a car body, there was some design choices that made that belie the perhaps the very the most functional body shape. Well, here's an interesting one. It's grids, but it's also construction geometry, and you have these objects that are voids. They're treated as solids in this this axon here, but they are voids in what is black here is the the data of a library. So this is a library, if you didn't know what a bibliothèque was, by Ome. And what you have are these voids that are cut out of the stacks being where the books are. And the voids are where other programs happen. You can have spaces where events can happen, reading rooms, etc. So these kind of objects are modeled and then suspended in space. There is an actual model of this. It's quite interesting. Didn't win the competition, but this idea of punching out solids from this kind of voids within this mass, you can see it in a number of projects. You can see it in some Stephen Hall projects. It's definitely got a life in architecture still, and there were ideas, especially the use of a spiral here in the center, that made its way later when OMA won the competition for the Seattle Public Library. So recapping our systems, hopefully you now know what systems are, if you didn't already, and what they mean specifically to architecture, and how architects use them to understand and create architecture. Lastly, if you liked some of the drawings and media that were created for this lecture, you can click on this link and get right at it. So all the Rhino files and Illustrator files and stuff like that are in there. So maybe you can learn a little bit about how the how the curves and stuff like that were organized in the file. And that's about it. I hope everyone has a wonderful day. And for my section, I'll see you in class.